Today I will be performing an experiment to see how an increase in mass will affect the force provided by your bicep while you are performing an isometric contraction, which is just holding still. So I'll be using an 8-pound dumbbell and then a 10-pound dumbbell. And I predict as we increase mass, the force provided by your bicep will also increase. So first, I'll stand here with an 8-pound dumbbell, just steady. And I can draw a diagram of that. So there will be your pivot point, which is your elbow. There's going to be a weight force pointing down, which will provide a torque from the weight. Weight equals mass times gravity. Our mass was 8 pounds, which divided by 2.2, that's 3.6 kilograms. 3.6 kilograms times 9.8 meters per second squared equals 35.28 newtons. So that means that there's going to be 35.28 newtons force down from the weight. So now there's going to be a force from the bicep pointing up, and so that's what we will be looking for. And so now we can say, because as I was standing here, it's not moving up or down, so it's just steady. So we can say that the torque from the bicep is going to equal the torque from the weight. So torque of bicep equals torque of weight. We can now use the equation R times F perpendicular for the bicep equals R times F perpendicular for the weight. So those are going to set equal to each other. The R for the bicep is going to be 4 centimeters, so that means that the bicep is attached to the elbow about 4 centimeters, times the force in the bicep, which is what we're looking for, equals the radius, which is, it's like the radial component. So I measured using this ruler, and I said it was about 27.5 centimeters, times the force from the weight, which is 35.28 newtons. And then we're going to solve for the force in the bicep. So that's going to be 27.5 times 35.28 divided by 4. And we can keep the centimeters because they're just going to cancel out. So we got a force from the bicep is 242.55 newtons. And that's going to be in the upward direction, so I'll put that on our diagram. And so now we can perform the same experiment to see how, if we add weight, which is now the 10-pound dumbbell, how that will affect the force from our bicep. So we can perform the same order, that we can say that the torque from our bicep is going to equal the torque from the weight. So now the weight mass, or the weight, is going to be the mass, which is 10 pounds, times gravity, which is 9.8. 10 pounds divided by 2.2 is 4.5 kilograms. So 4.5 kilograms times 9.8 meters per second is going to be our weight force of 44.5 newtons. So that's going to be the weight force that we use. So times the radial component of my arm, which was 27.5 centimeters. So we're going to set that up to equal the torque from our bicep, which the radial component is 4 centimeters, times the force from our bicep, which is what we're trying to find. So we're going to do 44.5 times 27.5 divided by 4 centimeters, which is 305.9 newtons. So as we can see, using the torque equation, we can see that as we increase the mass, which influences the force from the weight, as we increase that weight, we are going to also increase the force needed in our bicep. So we can also see that the force provided by our bicep is going to be way more than the actual weight in our hand.